Hello again, my dear students, and welcome to an extended video for the second chapter in our Analog Electronics 3 course. Maybe you remember in the previous two parts of chapter 2, we considered some analog filter design, starting with a simple inductor-less operational amplifier-based active filter, considering first stage or a single stage, and then a cascaded double stage, and then we proceed to what's called SAPs, or single biquadratic amplifiers design and switching capacitor in the previous part. Now we will going toward a new type or an additional type of filters, but it's very actually important and widely used industrially type of filters, which is tuned amplifiers. So our focus today will be toward understanding tuning amplifiers. Okay, I think you can now see my presentation slides, and we can also start, we can start operating the laser pointer. Okay, perfect. So, I'm sorry. Yes, I think. So this is the correct presentation. Okay, so our filter today is what's called a tuned amplifier filter. What is a tuned amplifier? A tuned amplifier is a double function amplifier that, from one hand, performs some sort of amplification for your signal. That's why we call it amplifier. But this amplification is not a frequency-independent amplification. It tunes a certain frequency, what we call the resonance frequency, to be highly or to be amplified and reject other frequencies. So generally, it's an amplifier with a frequency response having the shape or having the spectrum of a bandpass filter that pass a certain frequency with some sort of bandwidth and reject other frequencies. How we can implement such a bandpass filter? Maybe if we go to our reference, we will find this schematic for our operational amplifier, tuned operational amplifier. But you have to recognize, my dear students, that this represents the AC analysis for this operational amplifier. I think you spend at least two courses in Electronics 1 and Electronics 2 to understand the difference between making a DC analysis and an AC analysis for your transistor, either a MOSFET or a BJT. So basically, this AC analysis for a circuit reflects, let me shift now to a circuit looks like that. So here, this is the typical circuit. We have an input signal, as you can see here, my mouse. So we have an input signal directed to the gate, and we have a resistance, a coil, and a capacitor directed to some voltage VDD, and this is the terminal for the output, where your source is connected to a ground. Of course, for a typical operation, and this we will see it maybe later on in one or two slides from now, this gate voltage needs to be DC biased so that you can offset or DC offset your input voltage with a voltage greater than the threshold, so that you can guarantee that your transistor is on all the time. Otherwise, whenever your input voltage is lower than threshold voltage, it will turn off. Maybe we will see this 3 slides from now. So basically, this is the real circuit. But once you start to do an AC analysis for your MOSFET, as you know from your previous courses, you deactivate all DC supplies. So simply this VDD, this voltage, will be deactivated, which means that simply it will turn to ground, and then you get or you have the circuit you see here, which is basically this circuit. So this circuit is an output while considering an AC analysis. So in this case, we only have an input voltage. We only have an input voltage, which is in an AC directed to the gate. And then we have our MOSFET. Then we have resistance, capacitor, and a coil connected to ground because your VDD is now deactivated, and this is the output terminal. In this case, if you remember, my dear students, we use what we call the small signal analysis in order to investigate this signal. The small signal analysis was based on equalizing this MOSFET with its small circuit model. Let's remember together the small circuit model. So simply, this is a small circuit model. Here, this is the input and this is the gate voltage. As we all know that the current flowing into the gate is typically equals to 0 due to the oxide in the MOSFET. So we are equalizing the impact of a transistor by using this voltage-controlled current source with a factor called GM. And GM, if you remember, was calculated using the DC analysis parameter. And this GM is multiplied by the V input, which is typically VGS. Of course, VGS and V input are here the same because your voltage is connected between the gate and the ground, and your source is grounded. So simply V input and VGS are the same. So as you can see from this circuit, my dear students, now this equivalent voltage-dependent current source will flow in the equivalent impedance of the parallel equivalent of these three components: the resistance, the capacitor, and the coil. So simply, the voltage out, the output voltage, which is V out, is simply the current flowing in this three impedance capacitance multiplied by the equivalent impedance. The current flowing here, of course, is typically negative GM times V input because GM V input in this direction, so it will flow this in this direction from down to up. That's why it's in the negative polarity of the V output. That's why we will have a negative sign, and this is, of course, a common negative sign in our common source MOSFET configuration amplifiers. So the output voltage is simply negative GM times the Z equivalent. Or we can write it as negative GM V input, which is the current, divided by the admittance. If you remember from your circuit classes, the admittance, or Y, is the reciprocal of the impedance. Of course, whenever you have a parallel equivalent, it's easier to consider it in terms of admittance rather than in terms of impedance. So it's GMV over the admittance. What is the admittance? The admittance is the reciprocal of the component, and instead of having parallel, you will have a series or a plus condition. So instead of having R, you will have 1 over R. And instead of having SL or J omega L, as we already know from our previous classes, that J omega here is represented in the S domain by S. So instead of having J omega L or SL, we will have 1 over SL. And instead of having 1 over J omega C or 1 over SC, we will have SC. So it gives you that what we call the transfer function between the input and the output, which is simply GM over SC plus 1 over R plus 1 over SL. For better mathematical representation, you can make it, or you can just multiply the numerator and the denominator by S to get this equation, which is VM over V output over V input equal negative GM over C, S over S squared plus S over CR plus 1 over CL. And this will be your transfer function. The new thing here, with respect to what we already have understand from our electronics 1 and electronics 2 classes, usually in such circuit, our loads are in a form of a resistive load, RL and all these stuff. But now we have an RLC network in our loads. That's why we have this S domain function and its second order S domain function. So as we know from our previous classes in filters, the previous 2 classes, if you plot the frequency response of this S function, you can identify the nature of this filter. So simply plotting the S domain or the frequency response of this S square function, giving you this shape, or what we call the band pass filter. It calls a band pass filter because simply it has a frequency at which your gain is maximum, which is equivalent to what we call the resonance frequency. And as you can see here, that the resonance frequency will happen when omega equal 1 over root LC. Why this will happen? Because this is the point at which, let's consider it first from a mathematical perspective, and then let's consider it from a physical perspective. From a mathematical perspective, this is the point at which your function is maximum. As you can see, it's a maximum, it's a local maximum point. So you can easily find it by differentiation using mathematical analysis. Physically, at this point, the impact of your capacitor and the impact of your inductor will cancel each other. So if you go to see the gain or the transfer function when S is equals to when omega is equals to 1 over root LC, you will find it negative GMR, which simply means as if you don't have this capacitor and this inductor, and you just have a very basic circuit with only a resistance. Because at this resonance frequency, the equivalent impedance of the inductor, which we call it, if you remember from your circuit classes, we call it XL. The equivalent impedance of the capacitance is equalized by the equivalent impedance of the inductance. At this point, XL equals to negative XC. That's why the summation or the overall impedance between having a parallel XL and XC is simply equals to 0. And this leads to what's called a resonance frequency. So a resonance frequency is a frequency where the impact of the inductors and the resistors vanishes, and you only have your resistance leading to a maximum response, as you can see, with a gaining factor. So simply, if you have, or if you manage this negative GMR to be some number greater than 1, so the frequency, operating frequency omega node 1 over root LC will be amplified with a factor called negative GMR, which is your amplification factor at this wavelength or at this frequency. Another important parameter, which I think you already know from your communications as well, and from even our previous classes in the filters, is the bandwidth, which is typically the 3 dB or the 1 over root 2 bandwidth, which you can simply calculate by just going right and left with 1 over root 2 of the maximum value, and then you can get that your bandwidth is equals to 1 over RC. So here your bandwidth is dependent on both the resistance and the capacitance. And accordingly, we can define what's called the Q factor. I think the Q factor is, maybe you will consider this Q factor later on in your antenna classes, and also I believe we have it somewhere in our optical classes, which represents the sharpness of our response. So ideally speaking, if this band pass filter is an ideal impulsive filter, I mean you have a single frequency only pass with 0 bandwidth, then this Q will tend to infinity because simply your bandwidth is 0. And whenever you have, so this is actually the hypothetical value for Q, which represents the sharpness of your band pass filter. So whenever you have a higher Q, you have a better band pass filter, and once Q drops low, so this is a bad phenomenon, because simply that you have a wider bandwidth, which means that you pass more and more frequencies rather than the frequency typically you target, which should be 1 over root LC. So this is a 3 important parameters: the resonance frequency, the bandwidth, the Q factor, and of course as well as the gain for this tuned amplifier. You can visit this very interesting numerical example. It is also included in the reference. We can see together here. So it is required to design a tuned amplifier of the type shown in figure below, having a frequency of 1 megahertz. So this is should be the target resonance frequency, 3 dB bandwidth of 10 kilohertz, and a central frequency gain of negative 10. This is the gain. Of course, it's volt over volt, because maybe you to some extent you should be somehow impressed with why we are considering the unit voltage over volt, because sometimes the gain can be given in a unit of volt over millivolt, and this is simply when your input is a voltage and your input is in the millivolt range and your output in the voltage range. So basically the gain is V output over V input. So whenever the output is in the volt range and the input is in the millivolt range, so your unit will be voltage over millivoltage. But in all cases, here it's voltage over voltage with negative 10. The FIT available has a bias point GM with 5 milliampere per volt. Usually, I will consider, or I will give you the GM value, because as you see in this slide, we are only considering AC analysis. And in order to calculate the GM, you have to have a DC analysis. So either you should do a DC analysis to get the GM, or the GM will be given directly. And here we have also an additional output resistance. If you remember the output resistance from your MOSFET classes in electronics 1, so here in a 10 kilo ohm output resistance, the output capacitance is negligible, small, determine the value of RC and L. Okay. Okay, here, of course, what is negligibly small is the internal or the parasitic capacitance. We will consider this parasitic capacitance later on when we consider the RF tuner circuits, but for now, let's consider that we have only our output. So, simply speaking, the first is to consider is that you have this number, which is the gain. I think the gain is 10 volt, negative 10 over 10. So this gain is equals to what? This gain is equals to GM times R, but just take care, my dear students, that now you don't only have R, you also have R not parallel. So simply, if we go to this small circuit model, I can just add it to you now here. So I think, yeah, here. So it is as if you have a resistance here, which is R node. So simply your gain now will be negative GM R parallel to R node. You know GM, which is 5, I think. You know GM 5. You know the gain, which is typically negative 10. And you know R node as well. R node is given by 10 kilo ohm. So you can simply calculate the R, or the value of the resistance from these equations. That's just a direct substitution in this equation. So after considering the R, then you can go to the bandwidth. You know the bandwidth which is 10 kilohertz, and you have equation for the bandwidth which is 1 over RC. So basically, again, it's a direct substitution. Now you know the R and you know the bandwidth, so you can calculate the capacitance. And finally speaking, you know the resonance frequency was 1 megahertz, and you have the equation for resonance frequency was now C known, omega node known, which is typically 2 pi 1 megahertz. So you can calculate the L. So you can design your tuned filter with the knowledge of the frequencies, resonance frequency, the bandwidth, and the gain. So it's just a direct substitution question. Okay. So if you just remember when I start considering this circuit, yes, I told you that basically for the DC analysis, we have to have some sort of a DC biasing at this point, because simply this DC biasing is the source to guarantee a full operation of your MOSFET. Because simply speaking, if you have an input signal, which should be some sort of a sinusoidal input. So if this sinusoidal input is inputted to the gate, for example, considering threshold voltage for the MOSFET of about of about 1 voltage or whatever, that's basically mean that your MOSFET will only operate in this region. And whenever your input voltage is below the threshold, your MOSFET is basically off. So this is not a suitable amplifier. That's why we need to DC bias the input voltage with a certain DC biasing that allow a full 360 operation of your signal or of your input to be above the value, or to ensure that all the time the gate voltage is above the threshold voltage, and you ensure this full operation. Usually, if you remember, my dear students, we used to use this. Let me show it to you. Yes, here. This resistance, if you remember, this potential divider. So it's very simple. What you are going to do is simply you are going to DC bias. You have here a VDD, and then, of course, during a DC operation, these inductors will be considered as a short circuit, as you all know from your DC analysis. So simply speaking, what you are going to do is that you are going to superimpose, or you are going to DC offset this point with a value which is simply the potential divider of this RB2 and RB1. So simply the voltage here is VDD times RB2 over RB2 plus RB1, which very straightforward potential divider. But for this circuit, on the other hand, you don't need to have this resistance in the AC analysis. So you need to get rid of this resistance in the AC analysis. So you just need this resistance as a part of a DC biasing, but during the AC biasing, you don't need such a resistance. So what you typically going to use is you are going to use this, what we call RFC, or radio frequency shock. What is a radio frequency shock? It's a very basic use of an inductors in the tuned amplifier. So simply, all of you know that the equivalent impedance of an inductor is J omega L. So basically, in a DC operation, when omega is equals to 0, the equivalent impedance is 0. That's why we consider this L to be a short circuit in a DC analysis. But in a AC analysis, the impedance value starts to show some value, because now you have L and you have omega, then you have some value for omega L. What if we consider this omega L to be very, very, very high at the frequency of operation? So typically, I know that this amplifier will work at 1 megahertz. So I will put L somehow to have this omega L very, very high, which means that a value tends to infinity, or in other words, an open circuit. So in the DC analysis, this RFC, or the radio frequency shock, has no effect. It will be a short circuit, a wire. But whenever it turns to the frequency of operation, then it will turn to be behaving as an open circuit. So it just gives a shock to this branch and get it read out of the circuit. So basically, this turned to be an open circuit, and RB1 and RB2 will not appear in your AC analysis. So this is the first yes. Okay. The second point is we have to distinguish between these two capacitors, CC1 and CC2, and the capacitors used here. Because basically in electronics, typically here we are considering more toward RF electronics, we have two functions of a capacitor. One function is what we call a bypassing capacitor, which usually used in the cascading topology. That's why we have the word C here, which turns to cascading. So whenever you are cascading your circuits, I mean, you have different stages, as you can see here. So this is the input stage in the left, and this is the amplifying stage in the middle, and then this is the output stage in the right, and so on. You need to get rid of any DC component in your signal. So in this case, you use a capacitor because this capacitor in the AC operation, it will get rid of any DC effect. So whenever I do a DC analysis, I will simply consider the CC1 and CC2 as an open circuit. And this basically means that I divide the circuit into 3 parts. And each of these 3 parts is totally independent from a DC analysis perspective to the other ports. So, for example, when I calculate the voltage here, I said that this voltage is equals to VDD times RB2 over RB2 plus RB1, which means that I assume that there is no effect of this input signal on the DC biasing of this point. This is simply due to the bypassing capacitor. So these bypassing capacitors are designed in terms of a capacitance value so that they show an infinity impedance in DC analysis, and this is simply due to the 1 over j omega c. So when you have omega equals 0, the equivalent is infinity. Alternatively, in the frequency of the operation, in the operation frequency, or I mean when the resistance is equals to, when the frequency is equals to a value which is equivalent to. So when we are at the frequency of operation, this 1 over j omega c shows a very, very, very low value, so that you can consider this capacitor as a short circuit and that it has no effect. So it's a double function capacitor to show an open circuit during DC analysis and to show nearly a short circuit or a neglecting effect at the frequency of operation. Okay, so now we understand the role of these 2 inductors. We understand the role of these 2 capacitors. What about this circuit and this circuit? Definitely, this one is we already investigated, which a circuit used in the which is a circuit used in the tuning amplifier. So this is the source of a tuning amplifier, and this is the way where you have a resonance or 1 over LC resonance in order to guarantee that your resonance frequency will be amplified with a factor which called negative GMR, as we described together. By the way, we have another bypassing capacitor, which is CE, I forgot to mention, which has typically the same role or the same behavior. It's not the same role, I'm sorry. It typically has the same behavior as CC1 and CC2, because this will show an open circuit during the DC analysis, so that now you have a value or an emitter resistance, an emitter voltage value, this VE voltage, and alternatively in the AC analysis, this will behave like a short circuit. So if you remember this here, yeah, you will find this is a short circuit, but typically it's not a short circuit. It has a resistance value, but this resistance value will not be shown during the AC analysis because simply the capacitor will act as a short circuit, as I just mentioned, and then it will neglect or it will reject the effect of the resistance during the AC analysis. Now, a final stage is remaining, is this LC filter. If you go to make this LC analysis, you will find a very interesting behavior, that this LC analysis will end up with what we call a band stop filter. So it passes everything except some resonance frequency, which is L1C1. So you can simply understand it as, we just mentioned that at resonance, the equivalent of the capacitance and the equivalent of the resistance, the equivalent of the capacitance and the equivalent of the inductance cancel each other's. So that means that you don't have an impedance. You don't have XL or XC, because simply XL and XC reject each other's. And once XL and XC reject each other, that means you don't have anything. It's a band stop filter. So why we use this L1 and C1? This is a very interesting and this is a very important question as well. So simply we consider this what we can call a cleaning filter. The role of this filter is to clean your source from any noise before entering the amplification stage. Because as you can typically expect, whenever you have a noise and this noise is incident to an amplifier, basically this noise will be amplified as well. So in order to make sure that your resonance frequency will only pass to the amplifier and rejecting any expected noise to the system, you simply use this filter as an input stage to only pass your resonance frequency, and you can easily reject your noise by simply tune the value of L1 and C1, so you can adjust the band of your filter by simply adjusting L1 and C1. So this is the basic concept of a filter. But this topology has a very main drawback. And this is actually somehow we can consider it as a hidden drawback. Maybe we don't have the chance during this. Okay, so a very critical problem occurs in this design is related to what's called the parasitic capacitance. As you know, my dear student, this is what we call a bipolar junction transistor, which is typically, for example, for here, it's an NPN transistor. And this means that you have an NP junction here and NP junction here. The NP junction, and from our understanding to the principle of NP and NP junction, an NP junction in a reverse bias have what's called a capacitance effect. And if you return to the theory of operation of a bipolar junction transistor, you will know that in order to make this transistor in the active mode, which is the mode used for amplification, basically you make this base emitter junction to be a forward bias and this base collector junction to be a reverse bias. So when you make this base collector junction to be a reverse bias, that's simply mean you create a capacitance effect here. And the dangerous point here that this parasitic capacitance links the input to the output. So it seems like you have a bridge or a link between your input and your output through this parasitic capacitance. This is what we call a Miller effect. Actually, in this course, we are not going to consider the Miller effect or the parasitic capacitance in general in details. Maybe this will be for advanced courses, senior courses in year 4 under selected topics in electronic engineering. But it is important now to know the impact of this Miller effect due to the parasitic resistance between the base and the collector junction. There's a lot of topologies or architecture in literature that try to avoid or to minimize this Miller effect. And the idea here is very basic. The idea here is how to isolate the output in terms to the input. So a cascaded configuration may be a solution. As you can see here, you have, or there should be some sort of a Miller capacitance between this point and this point, but this point is not the output. So the Miller capacitance here is grounded, or the parasitic capacitance here is grounded. So you isolate the input with respect to the output by using a cascaded amplifier. So this amplifier, or this transistor, which is Q2, acts to isolate the output terminal to the input terminal. Another configuration here by using a common collector, common base cascaded amplifier. So here we have an input stage, and here we have the output stage, and both the input and the output stage are isolated, and here there is an intermediate terminal to link the input to the output. So again, you are playing with the same trick to isolate the input and the output so that you somehow eliminate the effect of the parasitic capacitance. So for example, here you have a parasitic capacitance, but with the VDD or the VCC. And here we have also a parasitic capacitance with a ground. So of course, you still have a capacitance effect, but the capacitance effect is no longer linking the input to the output. As I just mentioned, we are not going to go into high details related to this parasitic capacitance effect, but it's worth to mention at this point. Maybe it's kept for a later investigation in our next courses in general. That's all for this chapter. Thank you very much with this tuned amplifier chapter, and see you in the next chapter related to oscillators. Thank you very much.